Okay. Good morning, everyone. My name is Jiří Guth Jarkovský, and I work at a company that makes quantum computers. And that's what I will talk about today. First, though, I would like to spend some time talking about classical computers. So what do I mean by classical computers? Well, that could be anything. It could be your phones, your laptops. But in fact, most of classical computing these days is happening in huge data centers. So those are these buildings. It's a big warehouse full of GPUs built by companies like Amazon or Microsoft. And these data centers, they are just running 24/7, doing very heavy calculations on many different topics in many different fields. But if you look over time, this classical computing has grown a lot in the past couple of years. So this graph shows the energy consumption of classical computing. That's the green curve. And you can see how it compares to the world's energy production. That's the yellow curve. And we can see that in a couple of years, the green curve starts getting dangerously close to the yellow curve. So in other words, if we want to sustain the world's demand for computing, we need to come with some other way to do it, because the energy demands of all the training AI, doing all the calculation is already very significant, and it keeps going in that direction, and we need to do something about it. Now, when I talk about computing, what do they compute? There's a lot of topics, but I want to just focus on this one example that maybe is not very well known in the public. So this is about drug design. When you have a pharmaceutical company, they want to develop a new cure for cancer or Alzheimer's, they start by designing molecules. Like, it can be a simple molecule like this. And if they design the molecule, they want to see how it behaves, if it's toxic, how it interacts with other chemicals. And the best way to do it is to put it in a computer and simulate how this molecule, what happens there. But even though the molecule might look simple on a slide like this, in fact, what's happening there is very complex. Each of these atoms has a bunch of electrons. And in a molecule like this, all the electrons, they hybridize, they interact with each other. And since they are quantum particles, they follow quantum physics. So it's a very complex thing to simulate and to capture on a classical computer. And so here is where this classical computing is sort of hitting a wall, where if we start looking at bigger and bigger molecules, we are going to need more and more computing power. And generally, not just simulating molecules, the fact is that there are some problems that a classical computer just cannot efficiently solve. There are limits coming from math, coming from physics, that is just something that we cannot get around. Those are fundamental laws. That's how the computing works. And our current approach to that is just to build bigger data centers, to make bigger QPUs, more expensive ones, more power-hungry ones. But that is obviously not sustainable going in the future. So that is sort of why quantum computing exists. So in this, another chart is sort of showing what is happening here. So for some problems, like the molecule simulation, as you increase the problem size, the runtime for a classical computer goes up exponentially. But for quantum computer, the scaling, it also goes up, but it's not exponential. It's just linear or polynomial. Now, it should be noted here, this is very important, that this is just for some specific problems. This is not for all kind of computing. So I believe very strongly, we will see what happens in 50 years, that you will never have a quantum smartphone, for example. You will never make quantum slideshows, right? Because this is something that classical computers can do fine. But there are some problems, like what I showed previously, where the classical computers hit this wall, and we need something else to do that. One such problem, as you might have seen the headlines, has been solved by Google using their quantum computer. And here it says that they beat a supercomputer by 10 septillion years. Now, that sounds like a sci-fi thing, if you ask me, but it's actually a true statement. So what they solved was not simulating molecules. It was something that is not very practically useful for anything, but it's a problem that lies here in this regime on the right, where the classical computer computing time has shot up into septillion of years, whereas on a quantum computer, they needed just a couple of minutes, I think. But why do quantum computers work like this? What's the secret sauce? Well, it all comes down to the basics. So a classical computer relies on this basic building block called the bits, which is something that can be either 0 or 1, switch on and off. Now, maybe if you're programming or developing software, you don't come in contact with bits very much, but that is what is happening there at the lowest level. Whereas in a quantum computer, we have a quantum bit or a qubit, which can be in any superposition of the two states. Now, superposition means anything in between, but it's a little bit deeper than that. So in fact, there's like a whole sphere of all the possible states in between where the qubit can sort of be. Now, it has also some disadvantages. The main one is that if you want to figure out what is the state of the qubit, you look at it, it will collapse to either 0 or 1. So you lose the information and you destroy the state. But because of the superposition, qubits have this property that when you start adding them together, the number of these basis states will keep growing. And so, for example, for 3 qubits, there is already 8 different basis states. And so the 3 qubits together can be in any superposition of those. So you imagine like an 8-dimensional sphere. As you can think, it's already starting to get a bit complex. Now we can continue adding qubits, and then at one point when we get to around 50 qubits, we already have 2 to the power of 50 states, and that's already big enough that it's tough to emulate even for the best supercomputers. And because the scaling keeps going, when you add 1 more qubit, you would need 2 times more supercomputers. And you can kind of keep going until you get to a couple of 100 qubits, which is the size of the quantum computers that you can find right now in labs in various companies or universities. Now, how do we control the qubits? How do we do operations on them? Again, it's very similar to what is happening classically. So if you have studied electrical engineering, you might have seen diagrams like this. So this is, again, the thing that is happening in your classical computer at the lowest level, where you have the bits and doing some logical operations on them. So this is basically what all programs look like at the core. Basically, the same thing is happening with quantum computers. So now we have qubits, we apply some operations, which we call gates. Now these gates now can be a bit more complex because the qubits are a bit more complex than bits. But basically, this is what it looks like to write programs for quantum computers, and this is what I would do in my daily life. Now, at least that's the theory. In practice, we are currently in what people call the NISQ era of quantum computers, noisy intermediate scale. So intermediate scale means that the number of qubits is not too small, but it's also not very big. Again, if you think with classical computers, you have megabytes and gigabytes of memory and of computing power. Our quantum computers have a couple of hundred of qubits. But more importantly, at least in my opinion, the gates, the operations that we apply on these qubits are noisy. So they come with errors. And this, of course, limits the depth or the length of the algorithms that we can run. And so, this even if the gates are really good, like 99.9% good, the error sort of starts adding up really quickly, especially if you want to do some more complex computation, like a molecule with 40, 50 atoms. But a lot of companies, including IQM, have sort of charted the way forward. So this is our roadmap for the future. Right now we are in 2025 in the NISQ era. I don't know if you can see very well. We have quantum computers with 150 qubits, and as we move in time, we develop larger and larger chips. The number of qubits will go to thousands or to millions, and at the same time, we also work a lot on this QEC, so quantum error correction, where we need to start figuring out how to fix the errors with our qubits. So that is the basic summary of quantum computers. So if you had any doubts before today, I can assure you that they are real and they already exist all around the world, in Europe, in America, and in Asia. People build them and people study them because they have this very unique advantage over classical computing. There are these couple of problems that they can just fundamentally solve faster than what classical computers can do. And of course, it's now a very hyped field, but it's not only on the business side, very much also on the academic side. There's a lot of research happening. Every couple of months, there's a new paper of larger quantum computers with better performance, new algorithms, that kind of stuff. Now, there's, of course, still a couple of steps to take before quantum computers are ready for the industry. On one side, there's the application side, so that's the use cases, that's the programs that we run on the quantum computers. As I mentioned, there is a couple of use cases that they could help with, like optimization problems, simulation of molecules, some specific machine learning models, but it's definitely not exhaustive. There is also a lot of things that require heavy computation, like large language models, and it's not very clear if quantum computers can provide any advantage there and what the advantage would be, if it's in speed, if it's in accuracy, if it's maybe just the energy efficiency. There are some people who are saying that even if the quantum computers are not faster, they might be more energy efficient because they just work fundamentally differently. There's also the big question of the scale. Like with 300 qubits, you can do some interesting stuff for a science article, but you cannot really have any impact in the industry. And a very big topic is this error correction, which is fixing the errors in the gates, which for quantum computers gets very complicated very quickly. Now, if you are interested in the topics, there is some good news for you. There is a lot of online resources. You can watch YouTube videos, there's online courses provided by the companies because we need to sort of train the workforce because it's a big field. There's some very difficult things that we need very highly qualified workers for. Fortunately for us, some universities have started offering courses that are specifically in quantum computing and quantum technologies. And for the more competitive souls there are also hackathons to sort of try to show your skills in programming a quantum computer. Now, if you're a business leader or a decision maker, I think now, it is always the best time, second best time after yesterday, to start looking into what will be the impact of quantum computers, right? So when they come in 5, 10, 15 years, the impact will be relatively broad in quite a lot of fields, not just pharmacology, but anything in finance, logistics, machine learning. Basically, any field that relies heavily on classical computation right now could be impacted by the coming of quantum computers. But the devil is always in the details, in what exactly are the computational tasks, and if they can be sped up with the quantum algorithms. So yes, that was from me a bit of an overview of what is happening in quantum computing. Thank you very much for your attention.
Dámy a páni, Jiří Guth Jarkovský. Jiří, do you prefer having a short Q&A in English or in Slovak?
Both is fine. Já mluvím česky, ale jenom o kvantových počítačích radši mluvím anglicky.
Super, takže môžeme aj po česky, slovensky.
Môžeme.
Výborne. Taká otázka, teda dostávajú sa, už sú realitou tieto kvantové počítače, dostanú sa niekedy aj medzi verejnosť, že ich budeme vedieť používať v nejakej podobe, ako používame teraz?
Ano, určitě. Několik různých možností. Většinu těch kvantových počítačů, které v současnosti si například od nás někdo kupuje, tak si kupují univerzity a výzkumná centra, která umožňují, potom co se člověk zaregistruje, když tomu má nějaký důvod, tak umožňují přístup přímo k tomu kvantovému počítači. Můžete si pak s tím zkoušet programovat v uvozovkách nebo zkoumat, co se na tom děje. Kromě toho také firmy jako my, nebo například IBM, Google, myslím, umožňují nadšencům se zaregistrovat na jejich webových stránkách, založit si účet a používat kvantový počítač tak jako přes cloud.
Jasné.
Že sedíte doma ve svém pokoji a pošlete ten svůj výpočet k ním a ono to proběhne, nebo u nás v naší laboratoři, kde máme ty kvantové počítače a dostanete zpátky ten výsledek toho
Jasné, čiže ja viem takto outsourcovať cez cloud vlastne ten výkon toho kvantového počítača.
Áno.
Super. Ďakujem veľmi pekne, Jiří Guth Jarkovský, ešte raz veľký potlesk.
Ďakujem.